Okay, welcome everyone to this continuation of what is tropical geometry, part 9 already, and finally, the part where, or the theorem where I got really excited about tropical geometry. You might have different reasons, obviously, to like or dislike tropical geometry, but this one was the one that got me into tropical geometry, or not into tropical geometry, but more like I started to love it. I started to understand why this might be an interesting thing to study. And it's the Bezout theorem. So everything in tropical geometry, as I understand it now, is like mirroring algebraic geometry. And a classical theorem that I will recall for you in algebraic geometry is the Bezout theorem, and it's really beautiful. And then it's like, there's a special case. And then if you look in the special case, there's a special case of the special case. And then there's a special case of the special case of the special. And a lot of algebraic geometry was developed to kind of avoid those special cases. And you just don't need that in tropical geometry. It's kind of very, a lot of fun. So the classical Bezout theorem is essentially the following. You have two lines, and now we're doing algebraic geometry, so really just two lines, polynomial equations. They intersect somewhere. And so degree 1, polynomial, the line is of course degree 1. So here are the equations for the lines. Degree 1, and essentially 1 times 1 is 1, so they are supposed to intersect in 1 point, right? So two lines intersect in 1 point. I come back to the rest in a second. Here's a degree 1 thing, a line, and a degree 2 thing, a circle, and they intersect in 2 points. 1 times 2 is 2, right? Circle intersect, line intersects a circle in 2 points. If you do degree 2 things, degree 2 and degree 2, so a circle and a hyperbola, they intersect in 2 by 2 equals 4 things. And this is like the Bezout theorem, which I'm going to get at here, right? So if you have a degree k curve and you have a degree, so let's say k, and you have a degree L curve, then they are supposed to intersect in k times L points. All fantastic, and you just check that generically, and it's like works really well. And then there are all these special funny cases in the theorem. So kind of really beautiful theorem. The curves of a certain degree intersect in the product of the degrees. Very nice. But already for the lines, you notice that is not quite true. Because you could be like super unlucky somehow and have two lines that are parallel. These are supposed to be parallel. So they don't intersect. And essentially, to avoid that, you always want this intersection. People invented projective geometry, which really just means you're at this point at infinity, and the parallel lines kind of meet at infinity. This is a really bad picture, but I kind of get the point, right? In projective world, this is actually true. Two lines always intersect, right? And there's this one stupid special case that you can never avoid. If the two lines are the same, of course, it's not just 1 point, there are quite a few points. So two non-equal lines intersect in 1 point. And this is true in projective land. In the projective space, you are very happy. So the problem here, and the classical solution, the non-tropical solution is invent projective space, essentially. And that was literally what makes projective varieties a bit nicer. They have, well, all of these nice intersection type properties. Really just the tip of the iceberg here. Yeah, okay. And then you continue, well, circle and line, and then you realize that doesn't quite work. So for example, you could imagine something like, here's the degree 2 curve, a parabola, x squared plus 1, for example. X squared plus 1 has no real solution, right? The solution to x squared plus 1 equals 0 would be the complex unit, the I and minus I. And so here there's no intersection with the line x equals 0, right? So, and no projective land will fix that. What you really need to do is you need to go to the complex numbers. And then you actually have an intersection, obviously, in plus and minus I, and you have, again, your two intersection points back, right? So let me try that again. It's kind of, so the parabola and the line are supposed to intersect in 2 points. Here are all 2 points, similar as with the circle, but there's this fun special case where your field is not large enough, and you kind of need to work over C, not over R. So most of classical algebraic geometry is over an algebraically closed field. It's a bit nasty because we can't really draw that pictures anymore, right? So here we kind of need to invent projective space, and we need to work over C and not over R. Beautiful theorem gets a little bit of a nasty taste here, right? Not too bad, but a little bit, I guess. Similarly here, hyperbola intersects hyperbola, and there could be something like a degree 2 thing, so you could have a circle and another circle, or ellipse and a circle, and they're supposed to intersect in 4 points, right? 2 times 2. It's really nice to draw those pictures. But what could happen is, let's say you are really unlucky, and here's my circle, and your circle is just something like just touching my circle here and touching my circle here. Then you only have 2 intersection points, and there are several ways to kind of get rid of this. And let's say we just say they intersect generically, right? So you don't want kind of fun pictures where the big circle, let's say, and the small circle is just touching the circle. So no tangent type touching things, right? So it's already true here. My little blue line could, of course, just touch the circle, and then it's not quite true. So you want something like generically. Well, and I make generically a little more precise in a second. But then you get this Bézout theorem if you add all of these assumptions. So 2 complex projective, right? Complex numbers, we need algebraically closed. Projective, lines, you need projective space. Intersect generically in the product of degrees many points, right? Product of degrees many points. That's the classical Bézout theorem. And the tropical Bézout theorem almost reads the same. You just get rid of, you don't need any complex or projective. No, it just works. You still need generically, because you could still have the stupid situation where you choose a line and I choose my circle in a stupid way, something like that. And then we don't have the nice situation. Or you choose a line, something like that, and I choose my line to be exactly your line. Then we also have too many intersection points. So this generically intersect is something you just somehow can't avoid. Fine. But we at least get rid of the complex and projective bullshit. Yeah? And the proof is actually super easy in this case. So generically, this is a line, a tropical line. So tropical line, essentially you have some plateau here, and then you have two things here, right? So that's a line. And if degree 2 would be, well, this is degree 2, you have plateau here, 2 things here, 3 things here. And then degree 3 would be plateau, 2 things, 3 things, and whatever, 4 things, right? And so on. And you can easily just do the count. Let's overlay the pictures. So degree 1 and degree 2, if I do that generically, something like that, flop, and you see 2 intersection points. Well, but it could also go into here, and you still see 2 intersection points. Or it could go into here, and you still have 2 intersection points, right? So just the intersection points move to different spaces. You could be in here, could look like that, and you still have 2 intersection points. It's fantastic. It always works. You could go into here, do something like that, and you still have 2 intersection points. This is like very badly drawn, but you still have 2 intersection points. And that's essentially the proof. So not difficult to prove if you just keep in mind, that's not what I wanted to do. If you just keep in mind that our little curves have this fun pattern with a plateau, and then 2 and 3 and whatever, and you essentially just make the count and count the possibilities how one fits into the other. And it's just true. You don't need complex numbers. You don't need projective. The only thing you really need is, of course, if you just, that's not what I wanted to do. Of course, if you just choose your curve like very stupidly, like it goes right here over whatever touches it, then this is of course not true. So that's why we have this generically intersect. Okay, but otherwise, really, really nice. Now I'm not doing the same mistake, right? I have my little thing here, and I get 2 intersection points, no matter how I place my little line, and the same is true for any type of degree tropical curve, and that's the Bézout theorem. And I highlight the 2 features again: no need for complex numbers, no need for projective space, and also the proof is like really not that difficult in the end. It's just a combinatorial argument, and this was what makes tropical geometry so nice. It's mostly combinatorics. And the generically intersect is essentially but something like almost all of the time, right? So if I really have the situation with 2 lines, almost all choices, let's say I choose random coefficients, and I will have an intersection, right? Randomly, if I just draw random coefficients, it's completely impossible to just have 2 parallel lines. It's just not going to happen. It's one event out of infinitely many options, so that's not really going to happen. So really just the generic picture, that's what we want. So generically this will be true. If I draw generically to whatever, these guys in projective space, they generically intersect on my 4 points, and here if I draw generically my tropical line, it will intersect the tropical degree 2 curve here in 2 points. So that's what I mean by generically, it's like random coefficients in almost all cases, right? You generally want to get rid of those funny, stupid cases where whatever, something, the circle touches the circle or something like that. Anyway, I hope you enjoyed this video, and I also hope to see you next time.